There we go. We are live from room. What is our room number?
25.
We're live from room 220. Okay, so here's when we start class as usual. You see better that way or with the light on? Always better? No napping here in the front row. I had a couple of questions about some problems on web work that I wanted to do. Do you have some that you want to particularly ask? I'm taking them. What you got?
I have a couple, but the first one was about the shipping should be.
Okay, let me see if I can find it. There might be a way to show that up here. Let me see. There we go. It's us. Okay. And this was here. Do you know which number it was?
It was either 3 or 4,
Okay.
but I don't think it's this assignment.
Oh, wrong assignment. This one.
This was my other question.
We're going to try this one?
Yes.
Okay. Okay. Make that smaller. Nope, I don't want that. Come back. Come back. There we go. Didn't know how to talk to this thing. Oh, you son of a biscuit. That's going to be on tape, isn't it? Why these are so difficult. Okay, at noon, ship A. So I'm going to write on here. My pen, which is here. At noon, ship A. We got problem 4. Come on, baby. Yeah, there we go. Okay, at noon, ship A is 40 nautical miles due west of ship B. So ship A is here. Ship B is here. Okay, that's not helping. There we go. And this is 40 nautical miles. All right, what next? Is sailing west at 25 knots, which you're going to say is miles per hour. And ship B is sailing north. Okay, so we can't see that. At 20 knots. Okay. How fast in knots is the distance changing at 7 p.m.? So we start at noon. Fast. The distance between them changing at 7 p.m. We always need to have some sort of instant. Okay, so there's our problem. Is it big enough? Because I have a zoom feature here. Big enough, everybody? Okay, so the distance between them is right here. So in this right triangle, 3 things are changing. We've got the vertical distance, the distance west, and then the distance between them. So we're actually going to need 3 variables. So let's go with X, Y, and Z. X is the distance between the ships in the horizontal direction. Y is the distance between the ships in the vertical direction. And Z is the distance between them. And so we're asked to find a change in the distance between them. That's a dz dt. And these knots are miles per hour. So those are going to be the dy dt and the dx dt. And so, I guess I need to incorporate the 40. They start 40 miles apart. So let's let x be the distance traveled after 12 noon, so that the total distance between them here is going to be x plus 40. Okay? Y is the distance traveled north from noon. X is the distance traveled west from noon. So x plus 40 is that total length of that leg of the right triangle. So we've got a right triangle, three sides related. We'll be using the Pythagorean theorem. This leg squared plus that leg squared is the hypotenuse squared. So we're going to start with that, and then we'll see what we need after we take the derivative. So we start with x plus 4 squared plus y squared is equal to z squared. 40. Make that parentheses into there. There we go. X plus 40 squared plus y squared is equal to z squared. So that'll be our governing equation. We'll take the derivative with respect to t. So the first one, we're going to use the chain rule. We'll bring the 2 down, raise that to 1 power less, and now multiply by the derivative of what's inside, and that's where we get the dx dt. Now we go take the derivative of y squared and get 2y times dy dt. And then across the right-hand side, we have 2z dz dt. We have the dy dt and the dx dt. We're looking for the dz dt. So we need measurements for x, y, and z at the instant that we're talking about here. So we're going to get x, y, and z at 7 p.m. 7 p.m. is 7 hours beyond the start. And so let's figure out how far this ship has gone north in 7 hours. They're traveling essentially at 20 miles per hour for 7 hours. So do you agree that that length is going to be 20 times 7 is 140 miles? So let's draw the picture at 7 p.m. All right, so help me out with this leg. This one's going 25 knots. So in 7 hours, I have 7 times 25. Oh, gosh. How much?
175.
175? 7 times 25?
Yeah.
You're right. 175, but then I have to add the 40. So this is 175 plus 40, or, oops, that's a 5. How do I make that into a 5? 215. And now we're going to have to use the Pythagorean theorem to get the z. So this is going to be 215 squared plus 140 squared under the square root. So now I have my x, y, z, dx dt, dy dt, and we're going to find dz dt. We've got some extra 2's here that we can cancel. So let's do that. Let's get rid of some of those 2's and cut my numbers down just a little bit. So I'm going to divide everything by 2. And now I'm going to fill my numbers in. The x plus 40 was the 215. Dx dt is the 25. The y is going to be the 140. And dy dt is 20. Z we found to be this goofy number. And then we're looking to solve for dz dt. So I'm going to put this number in here. And so our last step is just to divide by that square root. So the distance between them is changing by this many miles per hour. Does that make sense? So in all of these, if we have some extra variables, we need to go to that instant and find what the situation is between our variables at that instant. You happy with that one? All right, let's try another one. What was the next one? Right before that? Okay. The altitude of a triangle is increasing at a rate of 2.5 centimeters per minute, while the area of the triangle is increasing at a rate of 4.5 square centimeters per minute. At what rate is the base of the triangle changing when the altitude is 10.5 centimeters and the area is 89 square centimeters? So we've got problem 3. Let me try to paraphrase all of that. Go back to the other one. There. Okay. We've got a triangle. And we've got an altitude that we're talking about here, and the base. So the altitude, the base, and the area are all changing. So let's call the altitude H, the base B, and the area of a triangle is 1/2 base times height. So that's our governing equation. Now we're going to try to pluck those numbers out of the paragraph. So let me look back in here. It says the altitude is increasing at 2.5 centimeters per minute. So dH dt is 2.5. The area is increasing by 4.5 square centimeters. dA dt is 4.5 square centimeters per minute. At what rate is the base of the triangle changing? So our job is to find dB dt. At the instant, when the altitude is 10.5 centimeters, and the area is 89 square centimeters. So that's the way I interpreted that. That we're given how fast the height is changing, how fast the area is changing. We want to know the rate of change in the base, when the height is 10.5 and the area is 89. So all three things are changing, the three letters A, B, and H. So we're going to have to read this equation in terms of the three unknowns and take the derivative. So do you see that on the right-hand side, we're going to need to use the product rule? Well, let's do it. The 1/2 is a constant. We can pull it out. We're going to take the derivative of this, and we get dA dt. Here's the constant I'm pulling out. The first times the derivative of the second, plus the second times the derivative of the first. Can you see that well enough? Did I make that too small? B times dH dt plus H times dB dt. All right, so when we look on that right-hand side, we're solving for dB dt. This is what we're solving for. Let's make sure we have numbers for everything else. We've got a number to put in for H. We have a number to put in for DH, DT. We're going to need B. How are we going to get it? Go ahead. Go back to the top equation at that instant. We're going to find B at this instant. So let's do that over here. So I know that area is 89. B we don't know, H is 10.5. So let's get rid of this 2 and divide by that. Multiply by 2, divide by 10.5. 2 times 89 divided by 10.5 is equal to B. Let's see, 2 times 90 is 180, so 2 times 89 is 178. So I have B is 178 divided by 10.5. I'll just leave it like there. We're going to put all of our numbers into our equation right here. So I have dA dt is 4.5. Here's the 1/2, our brand new value of B. Plus H. Oops, sorry, dH dt is 2.5. Put that in there. Plus H. H is 10.5. dB dt is what we're solving for. Anybody getting seasick yet? Okay, so I got to pull that dH or dB dt out of there. Let's get rid of this 2 by multiplying the 4.5 by 2, and we get 9. All right, move that over here. So I have 9 is equal to this number, 178 divided by 10.5 times 2.5 is equal to 10.5 times dB dt. Oops, I got too many equal signs. What is this supposed to be? That's a plus. So to get the dB dt, we have to subtract that number and then divide by that number. So I can write our final answer as 9 minus 178 over 10.5 times 2.5 divided by 10.5. So whatever that number is, 9 minus 17.8 divided by 10.5 times 2.5 divided by 10.5. Okay? All right, what else you got? Don't know what that's for. Oh no, don't know what that's for. Very last one. Okay, I need a new page. I need my very last one. Oops, where'd it go? Go back, go back. There you are. There you are. Very last one. Okay. We are given this formula for the concentration of drug in the bloodstream 3 seconds after this drug has been administered. And we are asked to estimate the change in concentration over the time period from 30 to 35 minutes after injection. So before I clear the screen, let me write down this formula. This is Weber problem 7. Okay, so let me write my formula down. We're given C of t is 0.12 t in the numerator, divided by t squared plus t plus 1. The concentration after t hours. So C is the concentration. T is in hours. And we want to estimate the change in concentration from 30 to 35 minutes after injection. Okay, so here's the formula we're given. Concentration, hours. We want to estimate the change in concentration from 30 to 35 minutes after injection. So I emphasize the minutes because T's in hours. So we've got to make our units agree. Take both of those time units and divide by the 60 minutes in an hour. And then we're estimating the change in concentration from T is 1/2 to 35 over 60 hours after injection. We're estimating the change in concentration. The exact change in concentration is denoted delta C. Where we could get the concentration in 35 minutes by plugging in the 35 over 60 for T. Then we can get the concentration in 30 minutes by plugging in 30 for T, and that difference is the exact change. So that's given by C of 35 over 60 minus C of 30 over 60. But the difficulty in doing that is the calculations. Taking those numbers and squaring them, adding, multiply by 0.12, divide, gives you a messy number. So instead, this problem asks us to estimate that change. And our entity that estimates the change in C is going to be called the differential in C. That's the DC. The differential in C was that last part in the equation of the tangent line. It's the derivative times the change in the independent variable. So DC is going to be C prime times the change in the time. Okay, so I can change in time like that. We're going to do that in hours. We're going to need C prime then. So let's use the quotient rule and take the derivative of that function. So we take the bottom times the derivative of the top, t squared plus t plus 1. The derivative of the top is 0.12. Minus the top, 0.12t, times the derivative of the bottom. That'll be 2t plus 1. All divided by the bottom squared. Do we dare simplify? I think we can simplify a little bit, so what the heck, let's do it. Let's bring it down over to here. I'm going to multiply out the numerator a little bit. We're going to leave the denominator factored. That'll be a 0.12 t squared plus 0.12 t plus 0.12 minus 0.24 t squared minus 0.12 t, all divided by t squared plus t plus 1 squared. So we can get rid of the 0.12 t's. They add each other out. This one, t squared, 12t squared minus 24t squared is going to give you a minus 0.12 t squared. And then I have plus 0.012 or 0.12 all over that denominator squared. And then to make my numbers easier for me to calculate, I'm going to factor out the 0.12 and write that as 1 minus t squared up here. Now the idea in this differential is that we do these calculations at the nice number. We evaluate C prime at the 30 minutes, which t is going to be a half, and then we multiply by delta t. So the elapsed time is 5 minutes. We'll put that number in as 5 over 60, which is 1/12. That'll take care of that 12 that I have factored out in front. Okay. So let's put that in now. So DC is going to be equal to this expression we have here, this derivative, but I'm putting in 1/2 for t, that's the 30 minutes, multiplied by the change in time. The change in time was, again, 5 minutes, or 1/12 of an hour. Yes. Okay, well, let's see what we can do. I'm going to cancel this 12 into that 12, but this is 12 over 100, and that's 12. So when I cancel them, I still have 1 over 100 left. This is 1 minus 1/4, so that's going to be 3/4. On the bottom, I have 1/4 plus 1/2 plus 1. 1/4 plus 1/2 is 3/4 plus 1 is 7/4. So here's what I said I was going to do. That cancels into that and leaves me 1 over 100. 1 minus 1/4 leaves me 3/4. And then I said that bottom added to 7/4, but then I've got to square it. Did I do my arithmetic correctly? 7/4 squared is 49 over 16. I'm dividing by 49 over 16, so we'll flip and multiply. And so I'll have 1 over 100 times 3/4 times 16 over 49. May as well quit. And this is going to be change in concentration. And that was units on that. Help me out here. What were the units on concentration? Milligrams per cubic centimeters. So concentration is increasing by roughly that many milligrams per cubic centimeter. Yes?
How did you know to plug into what happened?
Because when we're estimating, we want to pick the easier number, right? We don't want to estimate the 35 over 60. That was the messy number that gave us trouble to begin with. So we pick a nearby nice number to get the approximation. Got another one? All good? I'm going to go on to the section that we were talking about in absolute extreme values. And that was section 4.1. We got the long day today, the longer day today. So when we talk about section 4.1, it's going to naturally lead into section 4.2. In section 4.1, we're talking about having continuous functions defined on a closed interval. And we want to know where the largest value on that interval occurs and where the smallest value occurs. We call the largest value the absolute maximum of the function on that interval, and the smallest the absolute minimum. And the thing is, if you have a continuous function, you're going to be guaranteed both of those. You're going to have at least one value that's an absolute maximum and at least one value that's an absolute minimum. Then we'll take away the restriction of having it on a closed interval and put this function on an open interval, where you're no longer guaranteed that because the ends of the graph could continue forever and ever. So in those cases, when we're on an open interval, our interest will be in where the function has relative extreme values, a relative maximum based upon all the y values near it. Is this y value taller than the rest of them near it? And same thing with a relative minimum. So it's natural to progress from absolute extreme values to relative extreme values. But in section 4.1, we're talking about the absolute extrema. So I'm going to try to draw the function that I had up here last time. I forgot what it looked like. So it's going to be some function on a closed interval that's continuous. So let me draw it first. Let's I think I went down and kind of up and a sharp corner. And then something like that. I had arrows on it to begin with. This is some continuous function, y is equal to f of x. Put the x-axis down here and the y-axis. And I said where the tangent lines were horizontal, let's just label that as x1, x2. At the sharp corner, there's no tangent line, but that's a point of interest to us. So I have 4 places on here at which the derivative is either going to be 0 or there's no derivative. So here the derivative is 0. In these nice places, there's no derivative here. Horizontal tangent line, horizontal tangent line. The numbers at which the tangent line is horizontal are going to be the places where the derivative is equal to 0. The place where that sharp corner occurs is going to be where the derivative fails to exist. The numbers at which f prime is 0 or f prime does not exist are called critical numbers. for F. I'm thinking with a name like critical numbers, they're pretty important. They're going to be the key to finding absolute extreme values and relative extreme values. And when we get to graphing, they're going to be the key to helping us describe the shape of the graph. They're that critical. They're not kind of important numbers. They're critical numbers. So we've got to be able to take a derivative of a function and simplify it enough so that we can find where the derivatives are 0 and not defined. Now, in this function, I've got the ends going up forever. In order for this function to have an absolute max and absolute min, we've got to cut it off somewhere. So how about we put this point as a cutoff point, call that x value A, and then we ignore that. That's not of interest to us anymore. And then let's cut off this critical number. Let's not even consider it. Let's put x as B right in here. And so we don't care about that critical number because we're cutting off that part of the graph. And we're only interested in that part of the graph here between x is equal to A and x is equal to B. Well, that's not very effective. Do I have a color? Let's try coloring it green. I'm only interested in this part of the graph right here. So in that part of the graph, it looks to me like the very lowest part of the graph of all the y values on that green portion occur at x3, where there's no derivative. And it looks like the tallest one, I don't know, this looks like a little bit taller over here at x4. When we're finding the absolute extreme values of a function, though, we're not going to have the graph. We're just going to have the formula for the function. So what I need to find are all the critical numbers, get the y values there, but also find the y values at the two endpoints, and then see which is the largest y value. We'll call that the absolute maximum. And then the one that's the smallest y value will be the absolute minimum. Okay? So for a continuous function, y is equal to f of x, to find on a closed interval from x is A to x is B, there will always be an absolute maximum and an absolute minimum. You're guaranteed that. And how we find them is going to be relatively easy. You've got your function, you acknowledge that it's continuous on a closed interval, take the derivative, find all the critical points, keep only those in the interval, like here we would have thrown out x5. Find the y value at every one of those critical points, then find the y value at the two endpoints, and look at the size of the numbers. So I'm going to call that the candidates test. The candidates for the absolute extreme values are all critical numbers in the interval and the two endpoints of the interval. So we find the y values at all critical numbers in A, B, and compare those to each other and to f of A and f of B. Pick the largest, and that'll be the absolute max. The smallest will be the absolute min. So our job today is just to make sure that we can do all the algebra. So let's start with easy stuff like polynomials. Yes, sir?
Would the F1s be?
Yeah, that would be the f of A and the f of B. I want the y values. When we talk about extreme values, those are the y's. So we're getting the y values at all the critical numbers in the interval and the y values at the endpoints of the interval. Okay, so let's start with a polynomial, something that we can easily take the derivative of and easily factor. We might have some idea what the graph even looks like. Let's let f of x equal x cubed minus 6x squared plus 9x plus 8. And let's find the absolute max and the absolute min on the interval from 0 to 10. So what does a third degree polynomial look like? Usually it goes from left to right, up, down, up. Right? So we're anticipating having two critical numbers. Then we're going to lop off the ends of the graph at 0 and 10 and compare those y values. So take the derivative. Set the derivative equal to 0. We're not going to have any sharp corners because it's a nice polynomial, so we agree that it's continuous. So there should be both max and a min. Our derivative is 3x squared minus 12x plus 9. We can scale that down a little bit. Everything's divisible by 3. I'm going to set the derivative equal to 0, so then when I divide by 3, I don't have to worry about the 3 anymore, but I'll just factor it out in this step. Now, are there factors of 3 both with the same sign? Then add the negative 4. 3 and 1. So we're going to have x minus 3 and x minus 1. And now when we set each factor equal to 0, we get two critical numbers. X is equal to 3 and x is equal to 1 are those. Both of those numbers lie between 0 and 10, so they're both keepers. We're going to find the y value now at 3, 1, 0, and 10. So let's just do that in table form here. I want to use those x's, and I'm going to plug them back into f. Probably going to need some help here. 3, 1, 0, and 10. Let's do the easy one first. F of 0, 0 cubed minus 6 times 0 squared plus 9 times 0 plus 8 is just going to be 8. F of 1 is the next easiest one. 1 to any power is 1. So I'm going to have 1 minus 6 is negative 5. Plus 9 is a positive 4. Plus 8 is 12. F of 1 is 12. Let me get f of 3 over here. I might need to scribble that one. 3 cubed is 27. 3 squared is 9. 6 times 9 is 54. 3 times 9 is another 27. And then plus 8. But 27 plus 27 is 54. So that 54 minus 54 plus 8 says that f of 3 is equal to 8. And now f of 10. 10 cubed is 1,000. 10 squared is 100. Times 6 gives me 600. 9 times 10 is 90. And then plus that 8. So that's 498. I'm thinking 498 is the absolute maximum. And 8 is the absolute minimum. Okay? And it's okay for the absolute min to occur more than once. You're going to get one of each. It's also possible that if you have something that's horizontal, that your absolute max is the same as your absolute min. But we'd know that before we start the problem. Yes, sir?
So endpoints are not critical.
Endpoints are not called critical numbers, but they're candidates for the extreme values. So we can all handle polynomials. Let's try some other functions of greater interest to me. You like trig functions, don't you? Let's find the absolute max and the absolute min. Come on back down here, Paige. Woo! Come on, pencil. Let's see. F of theta is equal to the cosine of theta plus the sine squared of theta. And let's just worry about one period. On the interval from theta is 0 to theta is 2 pi. We know the absolute max and absolute min both exist because this is a continuous function. Cosine by itself is continuous. Sine is continuous, so sine squared is. And then the sum of two continuous functions is continuous. There's no breaks in this graph. We know the shapes of sines and cosines. There aren't going to be any sharp corners. So it's going to be places where the derivative is 0 that we need to collect. Take the derivative of that, and let's see if we can find the values of theta in 0 to 2 pi, which this is 0. Use the power rule on the sine squared of theta. Think of that as the sine of theta quantity squared. Bring the power down, raise it to 1 power less, multiply by the derivative of what's inside. We're getting two critical numbers inside this interval. Anyone tell me what your critical numbers are? Silence, silence. Let's see, what's the derivative look like? Here the cosine is minus the sine. And then here I said use the power rule. Bring the 2 down, raise this function to 1 power less, multiply by the derivative of what's inside. So we're going to set that equal to 0, and I'm going to solve this by factoring. We're going to pull out the common factor of the sine of theta. So if I pull out a sine of theta here, the first term will just be a minus 1. The second term will be 2 cosine of theta. Now we're going to set each factor equal to 0 and solve for theta. Actually, I think I'm getting 3 critical numbers. Sine of theta is 0, and negative 1 plus 2 cosine theta is 0. Other than 0 and 2 pi, sine of theta is 0 when theta is pi, correct? So it gives me the 0 and the 2 pi that are the endpoints, but also gives me theta is pi. Let's solve the next factor for cosine of theta. So let's add 1, divide by 2. So 2 more critical numbers where cosine of theta is a positive 1/2. What's the reference angle there in quadrant 1? Pi over 3. And cosine is also positive in quadrant 4. So which angle is in quadrant 4? Which multiple of pi over 3? Pi over 3? The 6 pi over 3 is 2 pi. So 2 critical numbers are at pi over 3 and 5 pi over 3 from that factor. So we've only listed the ones between 0 and 2 pi, including 0 and 2 pi. We need to now go back and find the value of our function at those 5 candidates. So we have 0, pi, 2 pi, that's a goofy looking 2, pi thirds, and 5 pi thirds. Okay, so f of 0 is the cosine of 0 plus the sine squared of 0. Sine squared of 0 is 0. Cosine of 0 is 1. F of pi, well, sine of pi is going to be 0, so it's just the cosine of pi. Who knows what the cosine of pi is? Negative 1. And then at 2 pi, it's the same as 0. So that's going to be positive 1. So now let's try pi thirds. Cosine of pi thirds plus the sine squared of pi thirds. We knew cosine of pi thirds was a 1/2. That means sine of pi thirds is square root of 3 over 2, and then we get to square it. So that's going to be a 1/2 plus 3/4. 2/4 plus 3/4 is 5/4. And then the last one is 5 pi over 3. Should get the same number, right? Cosine of 5 pi over 3 is still a 1/2. Sine of 5 pi over 3 is negative square root of 3 over 2, but we're going to square it. So that gives us 3/4 again. So we get the exact same value of 5/4. 5/4 is 1 1/4. So 5/4 is going to be our maximum, and negative 1 is our absolute minimum. So the big thing to point out here is when we're finding where the derivative is 0, don't just move the sign over and then cancel it, because you'll lose a critical number. Once you're canceling the sign from both sides, you're using the critical numbers where the sign was 0. Try to get your derivative factored when you set it equal to 0. Okay? Questions, comments, complaints? Complaints go right there, there. Okie dokie. Let's do, maybe this one's short enough to fit in here. Let's do the same instructions. And let's use f of x is x times e to the 2x. And our interval is from 0 to the natural log of 2. But let's first try to visualize what the graph looks like. Is it continuous? Are there going to be any places that the graph breaks apart? E to the x is continuous. Y is equal to x is continuous. The product of two continuous functions is continuous. So I'm thinking it's probably strictly increasing function, but we'll find out. Take the derivative using the product rule. Set the derivative equal to 0, but try to find where the derivative is 0 by factoring, if possible. I don't think we'll get any critical numbers in there. Maybe to make it interesting, let's make the exponent negative. I don't know. Let's leave it positive and see. No, let's make it negative. Change my mind. It's my class. I can do what I want to. Make that e to the negative 2x. So I'm thinking that'll give us a critical number in the middle. Probably didn't make my interval big enough now. We'll find out. All right, the product rule is the first times the derivative of the second. So you get itself times the derivative of the exponent. Then we got the second times the derivative of the first. The derivative of the first is just 1. So I can write that as minus 2x e to the negative 2x plus e to the negative 2x. And I'm going to factor out the e to the negative 2x. And so I'll have negative 2x plus 1. So that derivative is going to be 0 when e to the negative 2x is 0, or when negative 2x plus 1 is 0. Is e to a power ever 0? E to the x and e to the negative x are both strictly above the x-axis. So this first factor gives me nothing. This second factor says that 2x is equal to 1. So it gives me x as a half. So we have to know how big the natural log of 2 is. The natural log of 2 roughly 0.7. They have a calculator on them? What's up?
I got e to the negative 2x times negative 2x squared before.
Wait a minute, where did the x squared come from?
Yeah. I did the product rule and I thought,
There's the first. The derivative of e to the negative 2x is itself times the derivative of the power.
okay,
So I just have a single x. I don't have an x squared.
oh, yeah, okay.
Everybody check the natural log of 2 on a calculator?
Yes.
Roughly 0.7. So that critical number is in the interval. So now we've got to find the value of our function at the 3 points, at 0, natural log of 2, and at 1/2. Okay, so let's put that over here. The 3 candidates for the extreme values are at the endpoints and the critical number. F of 0 is 0 times e to the 0, so 0 times anything is 0. Here we're going to have the natural log of 2 times e to the minus 2 natural log of 2. And here we're going to have 1/2 times e to the minus 1. So let me see if I can estimate this. The natural log of 2 and e to the minus 2 natural log of 2 is the same as the natural log of 2 e. I'm going to keep the minus sign here, but bring this 2 up here and write that as minus natural log of 4. And write that as a natural log of 2 over e to the natural log of 4. What is e to the natural log of 4? It's just 4. So I have the natural log of 2 divided by 4. We said the natural log of 2 is roughly 7/10. So 7 over 10 divided by 4 is about 7 over 40. So this is roughly equal to. Where 1/2 times e to the negative 1 is like 1 over 2e. E is about 2.7. So that's roughly equal to 1/6. What's wrong? I'm putting him into here. All right. Let me make sure that we got that. We're going x e to the negative 2x. That's a big deal. That's we got to try to keep things organized for us. So, which is bigger, 7 over 40 or 1/6? 1/6 is bigger? Yeah, 1/6 is quite a bit bigger, right? Not quite a bit bigger. It's a bitty bit bigger. Let's see if I got any of these numbers on a calculator. Did I do anything on a calculator? No, I don't have any of them on a calculator. I'm going to guess. Let's be bold and brave. I'm going to say that this one's the max. And then 0 is clearly the min. I want to check on a calculator. They're pretty darn close, 7 over 40 and 1/6. So 1/6 is like 8 out of 48 compared to 7 over 40. I don't know. Fun with fractions. We should probably get a common denominator. Common denominator would be 240. So I would have to multiply this by 40. This is 40 over 240. I would have to multiply this by 6. So it's 42 over 240. Ugh. Still too close to call because I'm doing some serious rounding up here. That's not quite 1/6. So we'd have to check on a calculator. Check on a calculator whether 1/2 e to the minus 1 is bigger or smaller than natural log of 2 over 4. The old Desmos going up here. All right, so I want, what did I say it was, the natural log of 2 over 4? It's 0.17. And then 1/2 of e to the negative 1 is 0.18. Nailed it. So it's ever so slightly larger. So our max is at x is 1/2. Okay? Oh, those are hideous numbers. I don't want to do that one. Hideous! All right. Let's see here. Same instructions. Find the absolute max and min. We're going square root of x times x minus 5 to the 1/3 power on the interval from 0 to 4. You can have all kinds of funky exponents here. Negative exponents. So I suggest you check your derivative. See if you can write your derivative in positive exponents. We'll see. We'll see. I'll give you a break after you do this one. fraction here. Oh, this comes back in. Two orders on it. One thing you need to note is that this is a continuous function because the square root of x is a nice continuous function from 0 on out. And our endpoint starts at 0. The cube root is a continuous function, so the product of the two will still be continuous. But you know the derivatives are going to have negative exponents. So there's going to be places in here where the derivative fails to exist. That's going to be a sharp corner possibly, and also at the endpoint at 0. For that square root function, there should be no derivative when x is 0. So what we're doing to this thing called is we're taking a derivative and we're finding where the derivative is 0. What's the derivative of the square root of x? 1 over 2 square root of x, right? Where the square root of x is 1 over 2 square root of x, and we've already gotten that simplifying step done. Show up. All right, so I can see there might be some problem here doing the algebra, so let me catch up with you. Here's the product rule. The first term times the derivative of the second, so let's write that as 1/3 x minus 5 to the negative 2/3. The derivative inside is just 1. Then the other way, x minus 5 to the 1/3 times the derivative of the square root of x gives you 1 over 2 square root of x. So here's where I'm going to write everything with positive exponents. This 2 is going to be on the bottom. X minus 5 will be to the 2/3 on the bottom. Square root of x will be on the top. That is a 1/3, thank you. Okay. And then the second term, x minus 5 to the 1/3 divided by 2 square root of x. Okay, so we want to know where that's 0. I am going to split my fractions up and move one to the other side. So let's take this one to the other side, and I'll tell you why I can do that without losing any critical numbers. In the next step, I'm going to cross multiply, and that step will hold for all values of x other than 0 and 5. 5's not in the interval, and I already know that when x is 0, I have no derivative. So I'm not losing any critical points in the interval, right? This is not defined when x is 5. This is not defined when x is 0, so I can't multiply by 0, right? So I'm going to make a note that when x is 5 or 0, then the next step is not valid, but I don't care about either of those points. So let's cross multiply. And when I multiply this times this, I get negative 2x. And when I multiply this times this, I add exponents. The 2/3 power plus the 1/3 power is going to give me the x minus 5 to the first power. So on the right-hand side, I'm going to have 3 times x minus 5 to the first power. Multiply the right-hand side out. Put the x's together, so I have minus 5x is equal to minus 5. And when I divide by minus 5, I get x is equal to 1, is my only critical point. It would be 15, wouldn't it? Man, right here. 3 times 5 is 15, so divide by 5 and I get 3. 3 is my only critical point. And 0 and 4 are automatically candidates, so the absolute max or min has to occur either at 0, 4, or at 3. So we're going to go up here and plug them in. 0, 4, or at 3. If I put a 0, this first factor is 0. 0 times any number is 0. So f of 0 is 0. If I put a 4 in there, I've got the square root of 4 times negative 1 to the 1/3. A 1/3 power is a cube root. I can take the cube root of a negative number. The cube root of negative 1 is negative 1. So I have negative 1 times 2. F of 4 is negative 2. And then here I've got the square root of 3 times the cube root of negative 2. Well, I don't know how big that is. It will be negative because the cube root of a negative number is negative. So it's the same as minus the square root of 3 times the cube root of 2. So we've got to figure out whether that's bigger or smaller than negative 2, or smaller in terms of more negative. So I'm going to my Desmos calculator, hopefully. There it is. Let's check out square root of 3 times 2 to the 1/3. That's 2.18, and it'll be negative. So that's slightly smaller than negative 2 that we got for the other value. That makes that number the absolute min. And the biggest number in the list is 0. Okay? What if you have a continuous function and you have an open interval, and on that open interval, like the whole number line, your continuous function has only one critical number? What's your conclusion about what happens at the critical number? It turns. So it's either an absolute max or an absolute min. If continuous functions on an open interval have only one critical number, that's either its tallest point, and the ends aren't going to turn back around, or its lowest point. I don't know if that happens in my next example, but let's see if we can find all critical numbers for this function. And I'm not going to give you an interval, we're just going to define it on an open interval. Let's find all critical numbers of f of x is equal to the inverse sine of x minus 2x. You need to find where this thing has a derivative that's equal to 0. Now remember that the domain of an inverse sine are all numbers x between what and what? Remember, the domain of an inverse sine is the range of a sine. So what's the range of a sine curve? Between -1 and 1, right? So the domain of the inverse sine implies that x has to be a number between -1 and 1. So if this has a critical number, it has to be between -1 and 1. So take the derivative. Who remembers that formula for the derivative of the inverse sine? I thought you were 1 over the square root of 1 minus x squared. Very good. How many others of you knew that? Very good. The rest of you get on it now. And then the derivative of 2x gives me a 2. So set that equal to 0. Notice that f prime is not defined when x is 1 or -1, because those are endpoints. The derivative is never defined at the endpoints of an interval. Right? Those are the endpoints for the domain of the inverse sine, so that's the domain of the whole function f. Set that equal to 0, move the 2 over, cross multiply. Maybe to get rid of the square root sign, you can square both sides. Let's see if you can find a critical number between -1 and 1. Anybody at a critical number yet? You don't get a plus or minus? Square both sides. All right, if I move the 2 over, square both sides, I have 4 is equal to 1 over 1 minus x squared. Now I'm going to multiply both sides by 1 minus x squared. So I have 4 minus 4x squared is equal to 1. Subtract 4, and I'll have minus 4x squared is equal to negative 3. I'm going to cancel the 2 negatives. And so we get x squared is 3/4. So x is plus or minus the square root of 3/4. So we're getting 2 critical numbers. Square root of 3 over 2 and negative square root of 3 over 2. Okay? All right, I said I'd give you a break. Let me give you a break. Take about five to 5.5 minutes. Stand up, go to the restroom, run around the building. Just don't escape. Okay.
It was one of the earlier rates, I don't know why, but it was the one that had to do with angles. It was the kite example. Like the kite is 75 feet off the ground, and the angle is decreasing. The x was changing at like 4 feet per second.
All right, let me find it here.
That was 9 or 11. It was 11.
Oops, probably the wrong homework set. All right, we'll do it. We'll do it. Might not have the same numbers as you. We've got a question on this one, web work problem number 11. Kite 100 feet above the ground, stays 100 feet. It never gets any higher. It just blows further out. It's only moving horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 300 feet of string has been let out? So let me see if I can kind of fake a diagram here. Okay, so the kite is going to stay 100 feet above the ground. So initially it's here. I bet you've never flown a kite in your life. You have? Okay, good.
Like competition.
Kite competitions?
Yes.
What do you do?
You basically get all the strong boys in your grade to get one and make it run for you, so your kite goes the highest.
So that's how you win, by being the highest. Okay. Gotcha. Okay, this kite stays at 100 feet above the ground, but it's moving horizontally. So maybe in a few minutes it's over here. And then it keeps moving horizontally. So that, let's see, 100 feet above the ground, it's moving at 8 feet per second. That way. At what rate is the angle between the string and the horizontal changing? So you see how as the kite moves, that angle is going to get smaller, right? At what rate is this angle changing? Let's call that angle theta. So we want a d theta dt when 300 feet of string is being let out. So this is changing, and this distance here is changing. So we have 3 distances on our triangle changing. So let me go back to a particular instant and put some variables over what's changing. So the kite string, let's just call the kite string z. The horizontal distance, this horizontal distance is going to be the same as that horizontal distance, so let's call this one x. But this stays at 100, so I don't need a variable there. Sorry, yeah, that is 100. I don't need a variable there. I have that picture. Then the other thing that changes is the angle. So we can't just use the Pythagorean theorem. We need something that plays with the angle as well. So my unknowns in this picture are the adjacent side and the hypotenuse and an angle. So which trig function do you think would be a good one to use? Cosine. Cosine deals with the adjacent and the hypotenuse. So let's start with that as our governing equation, that the cosine of angle theta is x over z. I know I'm looking for d theta dt. I know dx dt. Dx dt is the 8. That's a particular measure for z, 300 feet of string. But I don't know dz dt. So I'm going to change my mind. I don't want z as part of my related rates equation because I don't have a dz dt. But I do have a dx dt. So instead of using that, I'm going to use a tangent function. And maybe the z will play a role in finding a particular measurement. So this is trouble because if I took a derivative, I'd eventually get a dz dt. So instead of using that one, let's start with that the tangent of theta is 100 over x. And let's take the derivative of that. That'll give me a d theta dt and a dx dt, and those are the ones that I have information about. So let's start here and take the derivative of both sides. What's the derivative of the tangent of theta? And then we have to take the derivative of the angle. This is the same as 100 times x to the negative 1. So when we take the derivative of that, we'll get a negative 100 x to the negative 2. I'm going to write that as minus 100 over x squared. And then we get our dx dt. So in order to solve this now for d theta dt, we're going to need to know either theta or the secant of theta, an x, and a dx dt. So we have to go to the instant when 300 feet of string is let out, and let's see if we can figure out any of these missing numbers. So at that instant, our picture looks like 300 feet of string here. It's still 100 feet tall. We can figure out x right here. And if we know x, then we can figure out the secant of theta without worrying about what theta is. Right? So do the Pythagorean theorem for that instant and find x. X squared plus 100 squared is 300 squared. So x squared is 300 squared minus 100 squared. So x is the square root of that. Well, 3 times 3 is 9. Here's 100 times 100. And then 100 times 100. So that's going to be 80,000, square root of 80,000. Square root of 80,000. So how about that's 100 square root of 8? Maybe? So we've got that number to go here. dx dt we have is 8. What about, at that instant, what is the secant of theta? Secant is the ratio of which two sides? Hypotenuse over adjacent. So the secant of theta is going to be 300 over 100 square root of 8. So that's just 3 over the square root of 8, which makes secant squared of theta 9 over 8. And now we got to go back up to our related rates equation. And we know all the unknowns except for the d theta dt that we're looking for. So let's fill them in. Let's see. I'm going to fill them in right here. I've got a little bit of room on the bottom. So putting in our numbers, secant squared of theta is 9/8. D theta dt is what we're looking for. Then I've got a negative 100. Then I've got x squared, so 100 squared of 8 squared. dx dt is 8. Looks like I can finish this. 9/8 d theta dt is equal to negative 100. This is going to be 100 squared. This will be an 8. That's going to cancel with this 8. So one of these hundreds cancels. So on the right-hand side, I have negative 1 over 100. So d theta dt is negative 1 over 100 times 8 over 9, which is negative 8 over 900. That's going to be radians per time unit, radians per second. The angle is decreasing at a rate of 8 over 900 radians per second. I like that problem. I had to dig deep, had to go find some stuff. I kind of like that. You're supposed to say at this point, yeah, I liked that one too. What do these little masks make you mute? You feel free to chime in and, you know, tell me how much you're loving this calculus stuff. I'll accept audible groans. It's a good one, though. Okay.
That is radians per second, right?
That will be in radians per second. Most of these, I don't think you need, if it asks for, if it's decreasing, I don't think you need to enter the negative sign. You can just put the number in web work since you're told that it's decreasing. Okay, so let's see. In section 4.1, we talked about finding critical numbers of a function and the role that they play in absolute, max, and extreme values of continuous functions. We take a little sidetrack here in section 4.2, and we talk about two pretty important theorems in the world of calculus. But actually, in your little calculus world, they're just going to be some standby theorems. For my math majors, any math majors in here? Not any yet? These theorems show up in proofs later on. So let me tell you what they say. We're still dealing with continuous functions. So imagine a continuous function looking like a string again. And I've got a continuous function and I put a little wiggle in it. And I got the two endpoints here, and then where did it wiggle? Well, the two endpoints, if I connect them with a line, will have a certain slope. And my graph has those wiggles in it. There's something called the mean value theorem that says somewhere the slope of the tangent line to the graph has the same slope as the slope to the endpoints. Then there's a sub-theorem related to that that says, suppose the two endpoints are at the same y value, so that the slope of the line connecting the two endpoints is 0, right? y2 minus y1 is 0. Suppose those two endpoints there are the same, then somewhere in there, the slope of the tangent line has to be the same as the slope of the line through the two endpoints, which means the slope of the tangent line is horizontal. Right? So they're essentially saying the same thing. And I'm going to draw the picture. And the second theorem that I mentioned, first theorem I mentioned was, here's my glasses, the mean value theorem, mean being average value. And the second theorem that I mentioned, we'll call the zero derivative theorem, but that'll be Rolle's theorem. We've got the mean value theorem and Rolle's theorem in section 4.2. Today's subject, section 4.2, we've got the mean value theorem, and we have Rolle's theorem. But both of them deal with a continuous function defined on some closed interval. So let's denote my continuous function as f of x. On some closed interval from a to b. So I'm going to draw you one. Let's see. There's our continuous function. Let's say that this is at x is equal to a, and this other endpoint occurs at x is equal to b. The mean value of this function is the slope of this line. The slope of that line has as its ordered pair at this endpoint a, f of a, and the ordered pair at this endpoint is b, f of b. The slope of the line through those 2 points, f of b minus f of a, divided by b minus a. Changing the change in x, that's called the mean value of f on AB. The mean value theorem says that for this particular function, there is at least one number, c, between a and b, at which the slope of the tangent line is the same as that mean value. There is at least one number, c, in the interval ab, for which the slope of the tangent line is equal to that mean value. So let's kind of eyeball this graph. It looks like I might have two different places where the tangent line can have that slope, maybe about right here, and maybe about right here. Agree? Why didn't I bring colors? Right here maybe, and right here in my picture. So it looks like there's two numbers that satisfy the mean value theorem. Then what Rolle's theorem says deals with the case where f of a is equal to f of b. We have a continuous function with the added condition that f of a is equal to f of b. And then all that would do is make this numerator here in the mean value be 0. So it says there's at least one critical number in the interval where f prime is equal to 0. Then there is at least one critical number in the interval from a to b. Because we'll have our continuous function, maybe something like this. F of b is the same as f of a. Which means that average value is going to be 0. Change in y over change in x will be 0 over the change in x. And so in my picture, places look like about here and here. I don't know how Rolle got his name on this theorem just by making one special case. I suppose you could say that maybe f of b minus f of a over b minus a is 7. Then there's somewhere in there where the derivative is 7, and now that's Steven's theorem. You pick another number and you can have your own theorem. That's kind of slimy for a Rolle there to steal that same theorem.
It's called Gibbs.
Gibbs. That one's mine. I got pi. Okay, so let's see how this works. Our job is going to be to find that one number c, or at least that one number, right? Find the number guaranteed by the mean value theorem for this function on this interval. So we're going to be solving this equation for this number c. Okay. Okay, so it's not going to be the calculus that's hard. The theorem seems pretty obvious. What's going to be the work for us, didn't bring any examples, is doing the algebra. All right, so here's my first example. Let's see if it fits in that little spot right there. I would like to have my pencil back. Who keeps putting my pencil over here? So our most common example of a continuous function is just a polynomial. So let's take a polynomial function and define it on a closed interval. So let's let f of x be 2x cubed minus x squared. And let's let the interval be from 0 to 2. And our instructions are verify that this function satisfies the hypothesis of the mean value theorem and find all the numbers between 0 and 2 that the mean value theorem tells us exist. So let's see. Oh, we need one more part in here. We've got to have a nice smooth function. Not only does it have to be continuous, it can't have any wacky places in it. So it's got to have a derivative that exists in that interval. Okay, so it's going to be something smooth. So let me add that to here. Let f be a continuous function defined on a, b, and differentiable. Continuous function defined on a, b, and differentiable. On the open interval from a to b. In other words, there aren't going to be any corner points in there. They're just nice smooth places. So that's true for both. So in this example, I know f is a polynomial. So it is continuous and differentiable, no matter what interval you give me. So since it's a polynomial, I know it doesn't have any crazy behavior. It's continuous and differentiable. That means the mean value theorem does guarantee me a number c, at which the slope of the tangent line is equal to the slope of the line through the two endpoints. Let's find that number c. I want you to find c for which f prime at c is equal to f of 2 minus f of 0 divided by 2 minus 0. I'll get us started. F of 0 is 0. What's f of 2? Well, 2 cubed is 8. 16 minus 4 is 12. So we've got 12 minus 0 over 2 minus 0 on the right-hand side. The derivative of f is 6x squared minus 2x. So we're solving 6c squared minus 2c. 6c squared minus 2c is equal to, what I say f of 2 was 12. F of 0 is 0. And then we still have 2 minus 0 here. So the right-hand side simplifies to 6. I've got a second degree terms equal to 6. We better get the 6 over and set equal to 0. So we're solving 6c squared minus 2c minus 6 is 0. We can scale that down a little bit by dividing by 2. 3c squared minus c minus 3 is 0. I'm thinking that that's not going to factor for me. So let me grab some paper here. This is where you get seasick. Yeah, there we go. There we go. There we go. Come on, stay down. We're going to whip out the old quadratic formula, aren't we? I didn't say there's nice numbers in the interval at which the derivative is equal to the slope of the tangent line, or equal to the slope of the secant line. I said there are numbers. So they may not be nice. I don't think they are here. So the opposite of b is -1, plus or minus b squared, -1 squared is 1, minus 4 times 3 times -3, all of that divided by 2 times 3. Let's see, 9 times 4 is 36, negative times negative is positive, so that becomes a square root of 37. My interval is from 0 to 2, so I think we better take the positive square root. Square root of 37 is a little bit bigger than 6, so this is somewhere in the neighborhood of 1/7. That is between 0 and 2. So I found it. There's that value of c at which the slope of the tangent line is equal to the slope of the line through the two endpoints. Okay. So even though there was a polynomial, we still got kind of some goofy numbers going on here. I'm sorry? Because we're given the interval from 0 to 2. Oh. So let's see how much algebra you got. What kind of algebra you got on your kiddies? One more of these, maybe. All right, let's try. Let f of x be 1 over x plus 1 on the interval from 0 to 2. So my question is f continuous and differentiable on the interval from 0 to 2? Is f defined at every single number between 0 and 2? And is its derivative defined for every single number between 0 and 2? There is one number in which f is not defined. Where is that? -1. And its derivative is not going to be defined at -1, but it's not in the interval. So the answer to the question is yes, it is. And so there should be a number c at which f prime of c is equal to the slope of the line through the two endpoints. So find c, so yep. So find c for which f prime at c is equal to f of b is 2, minus f of a is 0, divided by b minus a. When you're finding f prime, you don't need to use the quotient rule because the numerator is a constant. Just think of that as x plus 1 all to the -1 power. I'll make the derivative a little bit quicker. Terminal things. So I think that's the equation we're solving. That the derivative I got was -1 over x plus 1 squared. I guess I should have put a c instead of that x. Is equal to 1/3 minus 1 over 2 minus 0. Is that about where you started? So let's say that this x is a c so that it kind of agrees with what's going on here. So I'm going to have -1 over c plus 1 squared. 1/3 minus 1 is a -2/3. -2/3 divided by 2 is just a -1/3. So I can cancel the negatives, divide both sides by -1, then cross multiply. Then you have 3 is equal to c plus 1 squared. Right? Cancel the negatives, cross multiply. So 3 is equal to c plus 1 squared. What would you do next? Take square roots, plus and minus the square root of 3 is equal to c plus 1. Now subtract 1. Which of these two numbers lives in the interval from 0 to 2? Positive only, right? So our c is going to be the positive square root of 3 minus 1. Okay. That's 4.2. Either of these theorems guarantee a number c in AB at which f of c, f prime of c, is equal to f of b minus f of a over b minus a if f of x is equal to, oh, how about 3x plus the secant of x on the interval from -pi to pi. Do I know that there's some value at which the tangent line has the same slope as the line for the two endpoints for this particular function? What are the requirements for the guarantee to hold?
It has to be differential.
Differentiable and continuous between -pi and pi. Well, 3x shouldn't give us any trouble. So we're kind of thinking about the secant now. Well, the secant is a reciprocal function, so it's got a denominator. And we know we can never divide by 0. Is there a number between -pi and pi at which we're dividing by 0? Pi over 2, right? And 3 pi over 2, or yeah, 3 pi over 2 is too big, -3 pi over 2. So neither of these theorems guarantee that number, because at pi over 2 and at -3 pi over 2, f is not continuous, nor is it differentiable. So no, because the secant of x is not defined at -pi over 2 and pi over 2. So it's not continuous or differentiable there. On that interval. So there's no reason to take a derivative and set it equal to f of b minus f of a over b minus a, because quite likely there's not going to be any numbers. And we're taking a derivative and doing operations over an interval where things start to break up. Okay? So, I guess the next time you see this statement here is when you're going to be sitting in calculus 2. And we're going to be deriving a formula for arc length. And your calculus 2 professor is going to say, well, look at this expression, change in y over the change in x, as the change in x goes to 0. We're guaranteed by the mean value theorem that that's equal to the derivative somewhere in there. And you're going to say, yeah, I know that mean value theorem. We passed over it real briefly in calculus 1. Because that's all I'm going to say about that. Okay? What we're going to do in the next section is find critical numbers, look where the function has positive slope and negative slope, and identify our critical numbers as being relative maximums or relative minimums. So you need practice finding critical numbers, taking derivatives, finding where it's equal to 0. That's what I want you to do between now and Tuesday. And I'll try to put up another web work that has this stuff on it. I think I have one up there already. Maybe. I don't know.
Is there any wrong?
I think. I'll look. I'll do it. That's my job. So what do you think about doing things on the little screen? Is that boring? Does it hurt your eyes? Okay?
Good.
Okay? So I'm going to figure out a way that I can put a link to these on Blackboard. If you guys ever miss a class, I hope I have it recorded. If not, I've got the notes and I can scan the notes. Okay? All righty. Have a good rest of the weekend.
You too.
Because it's like Friday now.
Have a good day.
Thank you.